In this problem, we have a box of books with a gravitational force of 325 newtons. It moves with a constant velocity across the floor when it is pushed with a force of 425 newtons, exerted downward at an angle of 35 degrees below the horizontal. We want to find the coefficient of kinetic friction between the box and the floor. So we have a little diagram over here on the left that shows what the direction of this force is, slightly downward below the horizontal line here at 35 degrees. Now, because it says a constant velocity, that means that we are in equilibrium. Even though it's moving, all the forces are going to balance each other out. The first thing we want to always do is we're going to start with our free body diagram. So I'll draw my dot here, which represents my box of books. The force that's always present in our problems is gravitational force. So I'll draw that in and label it as Fg. The box of books is on a surface, so therefore there is a normal force. The normal force is perpendicular to the surface. That means that the normal force is upward. And there's also a frictional force. Now, because the books are moving to the right, the frictional force is going to be to the left. Friction is always opposite the direction of the motion. Now in this situation, it is a constant velocity, so the box of books are moving. Therefore, it is a kinetic friction that we're talking about. There is no string, rope, or cable, so there is no tension force, but there is an applied force, and that's what this arrow is representing here. The applied force is slightly downward at an angle, and that angle is 35 degrees. So we'll draw in the angle as well into our free body diagram. Next step is we always write down what we are given, any values that we know. First thing is that we have this 325 newtons. That represents the gravitational force. So I'll write down that my gravitational force is 325. Now, if we're given the mass, we have to solve for the gravitational force by multiplying the mass by 9.81. For this situation, we're already just given the gravitational force, so there's no conversion necessary. We're also given this 425 newtons. That is our applied force. That's how much we are pushing at the angle. And the last thing that we have here is what we need to find. And we need to find the coefficient of kinetic friction. And that is that mu sub k. Coefficient is the symbol mu. So the next thing that we want to do, whenever we're given here force at an angle, we're going to break it into its two components. I'm going to draw this on the diagram itself, the free body diagram itself for now. But we want to solve for the y component, and we also want to solve for the x component. And I'm labeling them y and x, just like I would in math class. X-axis is horizontal, y-axis is vertical. Now I'm going to redraw this here to help me out. So I have my 425 applied force. I want to find the x component. And I also want to find the y component. The angle is 35 degrees. So the first thing I'll do is I'll label my sides. The longest side is the hypotenuse. My angle is on the left. The opposite of left is on the right. So this is my opposite side. And then the adjacent side is the one left over. I have my SOHCAHTOA that I'll write out. I'll first solve for my x component, and to do that, that's my adjacent side, and I have my hypotenuse side, so I'm going to use cosine for my x component. I have that the cosine of 35 is equal to my x component divided by my hypotenuse, 425. So again, this here represents a number, cosine of 35. So I can either look that up on my trig table, or or I can type it in my calculator, the cosine of 35, and I get 0.819. I multiply each side by 425, and I get that my x component is 348 newtons. The next thing I'm going to do is solve for my y component. That is my opposite side, and I have my hypotenuse, so I'm going to use the sine. And again, this sine of 35 simply represents a number, and that number is 0.574. I multiply each side by the 425, and I get that my y component is 244 newtons. Now the next thing I'm going to do here is I'm going to redraw my free body diagram. I want to go back to this original. What I'm essentially doing is I'm replacing this applied force with its two components. I'm going to replace this applied force with its x component and the y component that I've just found here. So I'm going to redraw this free body diagram. I still have my gravitational force. I still have my applied force, or I'm sorry, my normal force. I still have my friction. And now I'm going to replace, I'm going to put it in as a dotted line just to show that they are the components, my x component and my y component. So I'm simply redrawing it. Instead of having the applied force, I have its two components instead. Like I said, we are in equilibrium. We're moving at a constant velocity, and that means that the force on the left and the force on the right are equal to each other. That's what equilibrium means. So I'm going to write that out. I'm going to write just the letters. The frictional force is equal to my x component. And so now that I have my x component, I also know my frictional force. Remember, I just solved for my x component. My x component was 348 newtons. So that is also my frictional force, 348 newtons. Now in the vertical direction, I used to say that the normal force was equal to the gravitational force. This is what I used to say. But I have a third force in the vertical direction, this y component. And what I have to figure out is which side of the equation does the y component belong? Does it belong with the gravitational force, or does it belong with the normal force? And for this, I look at the direction. The y component is down, just like the gravitational force is down. It is on the same side of the dot as the gravitational force. So therefore, the y component belongs on the same side as the gravitational force. If it would have been upward, then it would have belonged with the normal. But since it was a downward component, it belongs with the gravitational. So now I can put in my values. I know the gravitational force. It was 325 newtons. And I also know the normal force here. We calculated that in the previous part. We saw that it was 244 newtons. And those combined together balance out the normal force. So now I get that the normal force is equal to 569 newtons. Now remember my main objective though. My main objective is to get this coefficient of kinetic friction. There is only one formula on your equation sheet that has the coefficient of kinetic friction, and it is that the frictional force is equal to that coefficient times the normal force. We just solved for the frictional force, it is 348, and we just solved for the normal force, which is 569. So now we can place those values into our formula. And we divide each side by the 569. There it cancels out on that side. And we get that our coefficient of friction is 0.61. Now there is no unit for the coefficient of friction. It's one of the few things that we have that has no units, because if we look here, it is a Newton divided by a Newton, and the units cancel out.